quantum mechanics stands as a testament to the triumph of human intellect over the limitations of the senses. It is a theory that undermined the very foundations of classical physics and revolutionized our understanding of the universe. Developed in the early 20th century by some of humanity's brightest minds, the repercussions of their findings are still felt many years later. The origin of quantum mechanics can be traced back to the late 19th century, when physicists were grappling with the problem of blackbody radiation. The search for a solution to this problem was a catalyst for the development of quantum theory. The issue of blackbody radiation had long perplexed physicists, and its resolution required a radical departure from classical physics. This breakthrough was achieved by Max Planck in 1900, whose revolutionary insights inadvertently laid the foundation for quantum mechanics. Have you ever wondered why certain objects glow when heated? Or why the color of the glow changes as the object gets hotter? When a rod of metal is heated, we can feel the heat radiating from it. As the temperature of the metal reaches 600 degrees Celsius, it begins to glow dark red, turning to bright red at 700 degrees Celsius. If the temperature would increase further, the color would progress through orange, yellow, and finally white. This phenomenon is known as thermal radiation, an electromagnetic radiation emitted by a body due to its temperature. All bodies, and not just hot ones, emit such radiation and absorb it from their surroundings. At normal temperatures, that is below 600 degrees Celsius, the thermal radiation emitted by a body is not visible because most of the energy is concentrated in wavelengths much longer than those of visible light. As a body heats up, the amount of thermal radiation it emits increases, and the energy emitted shifts to shorter and shorter wavelengths. At about 600 to 700 degrees Celsius, there is enough energy in the visible spectrum for the body to glow with a dark red color. The rates at which the body emits and absorbs thermal radiation need not to be equal. If a body is hotter than its surroundings, it emits more radiation than it absorbs, and so it cools down. If it is cooler than its surroundings, it absorbs more radiation than it emits, and so it heats up. There is a special case, however, when the rate of absorption equals the rate of emission. In this case, the temperature of the body remains constant, indicating that it is in thermal equilibrium with its surroundings. One of the pioneers in the study of thermal radiation was the German physicist Gustav Kirchhoff. In December of 1859, Kirchhoff began his paper titled On the Relation Between the Emission and Absorption of Heat and Light to the Prussian Academy of Sciences with the following words. A few weeks ago, I had the honor of addressing the Academy with a memoir on some observations which seemed to me most interesting as they allow drawing conclusions on the chemical constitution of the solar atmosphere. Starting from these observations, I have now derived, on the basis of rather simple theoretical considerations, a general theorem which, in view of its great importance, I allow myself to present to the Academy. It deals with the property of all bodies and refers to the emission and absorption of heat and light. In this paper, Kirchhoff introduced a fundamental principle that would revolutionize the study of thermal radiation: the relationship between the emission and absorption of radiation by non-transparent bodies. The principle, known as Kirchhoff's law of thermal radiation, states the following. For radiation of a given wavelength and temperature, the ratio of the emissive power to the absorptivity of a body is a function of the wavelength of the radiation and the temperature of the body, and is independent of the body's size, shape, and composition. The emissive power, denoted by E, is the rate at which a body emits radiation energy from a unit area of its surface. The absorptivity, denoted by A, is a dimensionless quantity that measures the fraction of incident radiation absorbed by a body, taking values from 0 to 1. Analytically, Kirchhoff's law can be expressed as the following equation. Where f of lambda and t is a universal function that depends only on the temperature of the body and the wavelength of the radiation. To prove his theorem, Kirchhoff analyzed a system of two infinite parallel surfaces, denoted by S1 and S2, each with perfect reflectors on their outer sides. The reflectors ensure that no radiation is transmitted through the surfaces and the thermal equilibrium of the system is not disturbed. the surface S1 can only emit and absorb radiation of wavelength denoted by lowercase lambda, whereas the surface S2 emits and absorbs radiation of all wavelengths denoted by capital lambda. All radiation other than lowercase lambda emitted by S2 is reflected back by S1 and reabsorbed. Consequently, Kirchhoff limited his calculation to radiation of wavelength lowercase lambda. Let the emissive powers of S1 and S2 be E1 and E2, and the absorptivity be A1 and A2 respectively. Kirchhoff reasoned that S2 must absorb as much as it emits of the radiation of wavelength lowercase lambda, whether it comes from S1 or S2. Of the radiation power E1 emitted by S1, S2 absorbs this much power after repeated absorption and emission, where K equals to this expression. And of the radiation power E2 emitted by S2 itself, S2 absorbs this much power. At thermal equilibrium, the rate of emission must equal the rate of absorption, so the following relation holds, from which we find this expression, which essentially proves Kirchhoff's law. In 1860, Kirchhoff published a second paper in the German scientific journal Annalen der Physik, which translates to Annals of Physics, in which he extended his previous work, originally concerned with discrete wavelengths of radiation, to continuous spectrum of wavelengths. This led to the introduction of spectral emissive power and absorptivity, denoted by E lambda and A lambda, respectively. Kirchhoff's law of thermal radiation then takes the following final form. Kirchhoff also introduced the concept of a blackbody, an idealized body that absorbs all radiation incident upon it, regardless of wavelength or angle of incidence. When a blackbody is in thermal equilibrium with its surroundings, it is said to emit blackbody radiation. The term blackbody was inspired by Kirchhoff's observations of colored objects in the visible spectrum of radiation. He noticed that light-colored objects tend to absorb most visible radiation except for the wavelengths responsible for their perceived color, whereas darker objects tend to absorb all of the incident light. Therefore, the absorptivity of a black body is unity, A lambda equals 1, and its spectral emissive power is equal to the universal function. Later, Kirchhoff considered a cavity with perfectly absorbing, that is, black, walls heated to a uniform temperature T that encloses thermal radiation. He concluded from thermodynamic principles that if the cavity is in thermal equilibrium with the radiation inside the cavity must exhibit the properties of black body radiation. Experimental physicists realized this model using a body with a cavity that has a small opening to the outside. Radiation enters the cavity through this opening and undergoes multiple reflections off the inner walls until it is absorbed by them. If the area of the opening is much smaller than the total internal surface area of the cavity, very little of the incoming radiation is reflected back out. Essentially, all radiation incident on the opening is absorbed. In such a case, the opening, rather than the body itself, acts like a black body. Kirchhoff's interest in the properties of black bodies was motivated by the investigations of Joseph von Fraunhofer, who discovered dark lines in the solar spectrum that correspond to wavelengths at which the solar atmosphere absorbs radiation. Indeed, Kirchhoff's second paper was part of a study titled Investigations on the Solar Spectrum and the Spectra of Chemical Elements. Kirchhoff noticed that when light passes through the solar gas, the gas absorbs light at the same wavelengths it emits. This led him to the study of relationship between the emission and absorption of radiation. Kirchhoff himself emphasized the importance of finding the universal function, recognizing its numerous applications in diverse fields of physics, and the search for this elusive function became a central problem in the study of blackbody radiation for many years to come. In 1879, Joseph Stephan determined empirically that the energy radiated by a black body is directly proportional to the fourth power of its absolute temperature. Expressed mathematically, this relation is given by the following equation, where E is the emissive power of the black body, Sigma is a fundamental constant called the Stefan-Boltzmann constant, and T is the absolute temperature. In 1884, Ludwig Boltzmann provided a theoretical derivation of Stefan's relation based on electromagnetism and thermodynamics. Therefore, the relation is referred to as the Stefan-Boltzmann law. Before applying the laws of thermodynamics to blackbody radiation, Boltzmann derived two conditions that must be satisfied. The first condition follows from the relationship between radiation and the second law of thermodynamics, proposed by Adolfo Bartoli in 1876. Bartoli suggested that increasing a body's temperature in an enclosure through an adiabatic process by reducing the enclosure's volume required considering the pressure exerted by heat radiation to avoid violating the second law. Boltzmann used this result to conclude that the existence of pressure with the following magnitude, where U is the energy density of the radiation, was consistent with Stefan's law. The second condition states that the energy density of blackbody radiation must be given by this expression, where f of lambda is the universal function, E lambda is the spectral emissive power, and c is the speed of light. It is important to note that in the following years, physicists primarily focused on determining the spectral energy density of blackbody radiation rather than the more general universal function. We will adhere to this convention in our discussion. Following a derivation that resembles that of Boltzmann's, we consider the fundamental thermodynamic relation for a system in thermal equilibrium, where U is the internal energy of the system, T is the temperature, S is the entropy, P is the pressure, and V is the volume. Dividing the relation by the infinitesimal change in volume and fixing the temperature yields this expression. By employing the following thermodynamic identity, the equation becomes this expression. Since the internal energy is equal to the product of the energy density and the volume, we have this expression. And the equality becomes this relation. To determine the pressure exerted by electromagnetic radiation, Boltzmann turned to electromagnetism. Since EM waves carry directed energy, the relationship between the energy, denoted by E, of a unidirectional EM wave bundle and the momentum, denoted by P, is given by this expression. Now consider a right cylindrical bundle of unidirectional electromagnetic radiation of energy density U approaching a flat boundary with a direction of motion parallel to its cylindrical axis and perpendicular to the boundary. The volume of the cylinder is equal to the product of its cross-sectional area, denoted by A, and length, denoted by L. The electromagnetic energy in the radiation cylinder is equal to the product of the energy density and the volume, and the momentum of the radiation then is given by the following expression. The time it takes for the radiation to reach the boundary is equal to the length of the cylinder divided by the speed of light. The radiation exerts a force, denoted by F, on the boundary, which is equal to the momentum delivered to the boundary per unit time. Consequently, the radiation pressure at the boundary is given by the following expression. Therefore, the pressure exerted on a surface by unidirectional electromagnetic waves normal to its surface is equal to the energy density of the radiation. If the radiation is isotropic, that is, coming from all directions equally, most of the radiation hits the boundary at angles oblique to its normal. Therefore, the intensity of the incident energy per unit area is reduced below U by a factor of cosine theta, where theta is the angle that the axis of the radiation cylinder makes with the normal to the boundary. Similarly, the momentum delivered normal to the boundary is also reduced by a factor of cosine theta. Therefore, the pressure exerted by isotropic radiation falling on the surface averaged over all angles of incidence from 0 to pi over 2 is given by the following expression. Substituting the expression for pressure into the equation for energy density yields this relation. We can replace the partial derivative with the ordinary derivative in this expression. By separating the differentials, we obtain the following result. Finally, integrating this equation, we find the energy density of the blackbody radiation, where A, radiation, is the radiation constant. The value of the radiation constant can be measured experimentally and is related to the Stefan-Boltzmann constant by this relation, which follows from the following equations. The following graph is the blackbody radiation spectrum curve, a plot of spectral energy density as a function of frequency for a blackbody radiation. The area under the curve represents the total energy density. According to the Stefan-Boltzmann law, the energy density of blackbody radiation is directly proportional to the fourth power of the temperature. Therefore, as the temperature increases, the area under the curve should also increase. Conversely, as the temperature decreases, the area under the curve should also decrease. In the late 19th century, Germany experienced a dynamic period of industrial growth and scientific discovery. The steam engine and the development of the railroad network had transformed the country into an industrial powerhouse, and the invention of the telegraph had revolutionized communication. German cities expanded rapidly, with new factories, mills, and workshops springing up. Gas and electricity were increasingly used for lighting, heating, and power, and their demand grew rapidly. However, the lack of reliable methods and standards in the field of electrical metrology, where metrology refers to the science of measurement, hindered the development of the heating and illuminating industries. In 1887, private philanthropists Werner von Siemens and Hermann von Helmholtz, with the support of the Imperial German government, established the Imperial Physical Technical Institute in Berlin. The institute was founded to provide scientific and technical services to the industry and government. Its tasks included the calibration and certification of measuring instruments, the testing of materials, and the development of new technologies. The institute was also responsible for the standardization of units of measurement, a task particularly important for Germany's rapidly growing industrial sector. The institute was tasked with developing a new standard for the temperature based on an absolute temperature scale. It was headed by Helmholtz, who appointed many physicists to the institute. Otto Lümer, who led the optical laboratory from 1887 to 1904, Wilhelm Willy Wien, who worked at the institute from 1890 to 1896 and was its leading theoretician and experimentalist, and Ferdinand Krulbaum, who worked with Lümer from 1891 to 1901. Additionally, many physicists visited the institute to conduct experiments and research. Ernst Springsheim, who volunteered from 1893 to 1904, and Heinrich Rubens, who became a guest worker at the institute in 1896. The conceptual work of the institute was based on the earlier theories and discoveries of Kirchhoff, Stefan, and Boltzmann. In 1893, Wien applied the Stefan-Boltzmann law along with principles of electrodynamics and the second law of thermodynamics to derive the energy density of blackbody radiation. Wien considered radiation contained in an enclosure with a perfectly reflecting mirror on one wall. The mirror moved slowly toward the opposite wall, compressing the radiation and changing the energy distribution of the radiation. Two effects would cause this change. First, the energy in each wavelength interval would be increased, corresponding to the wall doing work on the radiation. Second, the wavelength of the radiation reflected from the moving mirror would be decreased by the Doppler effect, which would transfer the corresponding energy from one wavelength interval to another. By considering these two effects, Wien arrived at the following expression for the spectral energy density of blackbody radiation, where phi is a function of a single variable, the ratio of frequency to temperature. As a consequence of this relation, the ratio of any arbitrary frequency to its corresponding temperature is a constant. Or, expressed in terms of wavelength, the product of the wavelength and temperature is a constant. This is known as Wien's displacement law because it shows how the curve for spectral energy density shifts with temperature. Lummer and Pringsheim confirmed this law and found the numerical values for the constants as follows. A special useful case of this law is when we consider the peak of the curve, which is the frequency at which the spectral energy density is maximum. This frequency is given by this expression. The following animation demonstrates how the peak of the curve shifts with temperature according to Wien's displacement law. If the temperature of the blackbody is increased, the peak of the curve shifts to higher frequencies. Conversely, if the temperature is decreased, the peak shifts to lower frequencies. This is the reason why hot objects glow with different colors as they are heated. The peak of the curve corresponds to the frequency of light that is most intense in the emitted radiation, and the color of the light is determined by this frequency. If the temperature is below a certain threshold, the peak of the curve is in the infrared region, and the object does not emit visible light, yet it still emits radiation, and we can feel the heat radiating from it. In 1894, Wien derived the displacement law on a more rigorous basis and showed that, as a consequence of Kirchhoff's law, blackbody radiation could be defined as a condition of stable heat equilibrium. From this statement, Wien concluded that once the blackbody's spectral energy density distribution was known for any given temperature, the temperature for all energy distributions could be determined. In the spring of 1895, Friedrich Kohlrausch succeeded Helmholtz as the director of the institute. He was skeptical of Wien's theoretical work, believing it to be too abstract. However, he agreed to Wien's request to allow the optical laboratory to implement the test of his displacement law as a regular part of the institute's work, presumably because he believed it would lead to the establishment of in-demand unit of luminosity. In June of 1896, using seemingly precarious experimental data of Friedrich Paschen of Hanover University and his own theoretical conjectures, Wien declared the precise form of the function phi to be the following expression. And so the spectral energy density of blackbody radiation is given by the following relation, where A and B are constants obtained by fitting the distribution to experimental data. This distribution is known as Wien's distribution law. Lord Rayleigh commented the following in 1900. Viewed from the theoretical side, the result appears to me to be little more than a conjecture. Nevertheless, it quickly gained experimental support because it fit the existing experimental data better than any other previously proposed law. This is the curve of blackbody radiation that experimentalists obtain down to a certain lowest frequency that could be measured at the time. The red curve represents Wien's distribution law, and as you can see, the curve of the distribution fits the experimental data very well and is almost indistinguishable from the data. Integrating Wien's distribution law over all frequencies should give us the total energy density of the blackbody radiation. This integral is given by the following expression. Substituting the expression for the spectral energy density into the integral, we obtain the following relation. To solve the integral, we make the following substitution. Substituting these into the integral, we obtain the following expression. The integral is a standard one, and it can be evaluated to give the following result. Substituting this into the expression for the energy density, we find the following result. According to the Stefan-Boltzmann law, the energy density of blackbody radiation is equal to the product of the Stefan-Boltzmann constant and the fourth power of the temperature. Cancelling the temperature from both sides, we find the following expression for the Stefan-Boltzmann constant in terms of Wien's constants A and B. In 1897, Paschen, as well as Lummer and Pringsheim, largely confirmed the validity of the Stefan-Boltzmann law. The following year, Dummer and Kurlbaum announced their realization of the blackbody. Their device, an instrumental breakthrough 3 years in the making, consisted of a thermocouple placed inside a completely closed platinum cylinder whose blackened inner walls could be brought into thermal equilibrium by electrical means. This device was superior to previous Blackbody realizations and allowed more precise validation of the laws. Loomer and Kurlbaum soon reported improvements in their Blackbody that allowed reliable measurements up to 1900 Kelvin, confirmed the Stefan Boltzmann law in the range of 90 to 1700 kelvins, and attempted to use it to establish a unit of luminous intensity. It was now time to challenge Wien's distribution law using the new device. Paschen believed he had experimentally confirmed Wien's distribution law. However, the experimental results obtained by Loomer and Pringsheim contradicted Paschen's findings and cast doubt on the validity of Wien's law. They found that at higher temperatures and longer wavelengths, which had not been previously studied, the distribution law deviated from the experimental data. The year 1900 marked a turning point in the Institute's study of blackbody radiation. Loomer and Pringsheim obtained experimental results for even longer wavelengths and observed greater deviations of Wien's law. This work, together with the theoretical work of Lord Rayleigh, led Loomer and Eugen Jahnke to propose a new empirical formula that covered the entire range of measured wavelengths and temperatures. However, the relatively limited range of wavelengths used in Loomer and Pringsheim's experiments were not sufficient to establish a precise law for blackbody radiation. Rubens developed a new method of residual radiation of rock salt in collaboration with Ernst Nichols. This method allowed them to eliminate all radiation except that of a desired narrow band of wavelengths. Later, in 1900, Rubens and Kurlbaum used this method to demonstrate conclusively that Wien's distribution law is invalid at increasingly higher temperatures and longer wavelengths. As you can see from the animation, Wien's distribution law deviates substantially from the experimental data at lower frequencies. At this critical point, the story enters a new phase with the arrival of Max Planck, whom we will discuss in the next part. Before that, we will explore the Rayleigh-Jeans Law, another attempt to derive the spectral energy density distribution of blackbody radiation. Lord Rayleigh used a distinctive approach, often considered classical in nature, to derive the spectral energy density distribution of blackbody radiation. In 1900, Rayleigh published a brief paper titled Remarks upon the Law of Complete Radiation, in which he suggested applying the equipartition theorem. He went on to derive the following relation. Without evaluating the constant C1, Rayleigh also realized that this relation should be interpreted as a limiting law. The suggestion is then that the given law, rather than Wien's distribution law, may be the proper form when the ratio of temperature to frequency is great. To suppress the catastrophic high-frequency behavior, he introduced an exponential cutoff factor and rewrote the relation as follows. This expression became known as the Rayleigh law. As early as 1900, Rubens and Kurlbaum, along with Loomer and Pringsheim, discovered that this law did not match experimental data at high frequencies. On May 18, 1905, the scientific journal Nature published a paper by Rayleigh in which he revisited this law and attempted to calculate C1, but made a mistake in the process. At the time of the publication, James Jeans was also working on the problems related to the equipartition theorem. In a paper titled On the Partition of Energy Between Matter and Ether, which he was preparing for submission to the scientific journal Philosophical Magazine, Jeans read Rayleigh's recent paper, where Rayleigh raised a number of questions centering on the failure of the law of equipartition of energy when applied to blackbody radiation. Responding to Rayleigh's questions in a postscript dated June 7, 1905, to the paper Jeans had by now already prepared, he pointed out that Rayleigh's calculation of C1 was incorrect and provided the correct value. Rayleigh acknowledged Jeans' correction in a letter to the editor of Nature published on July 13, 1905. The corrected law became known as the Rayleigh-Jeans Law. In his derivation, Rayleigh imagined a cube-shaped cavity. The cavity is uniformly heated to temperature T, causing its walls to emit thermal radiation that fills the interior. Recall that blackbody radiation is the radiation emitted by a blackbody at thermal equilibrium. To maintain this equilibrium, the walls of the cavity must be perfectly reflective, so that no internal and external radiation can transmit through the walls. The electromagnetic radiation within the cavity can be decomposed into three orthogonal components, corresponding to the three spatial axes x, y, and z. Since the opposing walls are parallel, these components can propagate without interference and can be analyzed separately. Therefore, we can simplify our analysis and focus on a single component of the radiation. Let's focus our attention on the x component. Let's assume that the side length of the cube is L. Since all radiation is reflected when it reaches the walls, the amplitude of the waves must be zero at the walls. This condition is satisfied by standing waves, which are waves that oscillate in place and have nodes at the walls. The amplitude of an electromagnetic wave is described by the electric field vector E. Since electromagnetic waves are transverse, the electric field vector oscillates perpendicular to the direction of propagation. Therefore, the electric field vector is parallel to the walls. It follows that the electric field vector is equal to 0 at x equals 0 and x equals L. One material that fulfills this condition is a metal. Metals are effective conductors of electricity with free electrons that can easily move in response to an electric field. When there's a non-zero electric field component parallel to the wall, the free electrons move in response to the field, creating a current that generates a magnetic field which opposes the original electric field, effectively cancelling it out. For further analysis, we may assume that the cavity walls are made of a metal. The standing wave shown on the screen is the first or fundamental harmonic of the standing wave. There are higher harmonics of the standing wave that can also fit into the cavity. As you can see, the only possible standing waves are those whose wavelengths lambda are such that an integer number of half wavelengths fit into the length L of the cavity. The first harmonic of the standing wave has a length of 2L. The second harmonic of the standing wave has a length of L. And the third harmonic of the standing wave has a length of 2L over 3. The nth harmonic of the standing wave has the following length, where Nx is the number of half wavelengths that fit into the length L of the cavity. The possible values of Nx are as follows. We can apply the same reasoning to the y and z components of the radiation. So the radiation has nodes at the walls in all three directions. The possible wavelengths of the standing waves in each direction are given by the following expressions, where Nx, Ny, and Nz are the number of half wavelengths in the x, y, and z directions respectively. Suppose now that we are interested in a wave in an arbitrary direction. We must find the number of half wavelengths n that fit into that direction. To do so, we may imagine a three-dimensional space whose coordinate axes are Nx, Ny, and Nz. Each point in the space corresponds to a permissible set of values of Nx, Ny, and Nz that correspond to a single value of n. A vector n from the origin to a particular point represents a standing wave in a certain direction with a wavelength lambda. The magnitude of the vector n is given by the following expression, which follows from the Pythagorean theorem. This equation represents a sphere with radius n in the n space. The sphere corresponds to all different possible permutations of Nx, Ny, and Nz that correspond to the same single wavelength lambda. In such a case, the possible values of Nx, Ny, and Nz are as follows. The reason why the zero values are included is because it is possible for any two of the values to be zero and the third value to be non-zero. Now we have to find the number of standing waves in the cavity with wavelengths between lambda and lambda plus d lambda. This number is equal to the number of points in the n space whose distances from the origin are between n and n plus dn. These points lie within a spherical shell with radius n and thickness dn. The volume of the spherical shell is given by the following expression. Since we are interested in the non-negative values of Nx, Ny, and Nz, that lie on the octant of the sphere in the first quadrant, we must divide the volume of the spherical shell by 8. Moreover, electromagnetic radiation possesses two polarization states, so we must multiply the number of standing waves by 2. Therefore, the total number of standing waves in the cavity with wavelengths between lambda and lambda plus d lambda is given by the following expression. Interestingly, this is where Rayleigh's calculation went wrong. He considered all values of nx, ny, and nz, not just the non-negative ones. This resulted in overcounting the number of standing waves in the cavity. Let's express the number of standing waves in the cavity as a function of frequency instead of as a function of n. We obtain the following relations, which follow from the following expressions. Substituting these into the expression for the number of standing waves, we obtain the following result. The cavity volume is given by the following expression, which means that the density of standing waves with frequencies between nu and nu plus d nu is given by the following expression. Rayleigh's next task was to find an expression for the average energy of a single standing wave in the cavity. According to electromagnetism, the energy of an electromagnetic wave can range from 0 to infinity, with the average value being proportional to the maximum value of the electric field strength. However, for a system containing a sufficient number of identical physical entities in thermal equilibrium at temperature T, the average energy of each entity is determined by the equipartition theorem of energy, which states the following. The average energy per degree of freedom of any classical body, such as a molecule of an ideal gas, which is a member of a system of such bodies in thermal equilibrium at temperature T, is kT over 2, where K is the Boltzmann constant. Rayleigh noted that a one-dimensional wave always has 2 degrees of freedom, one corresponding to potential energy and the other to kinetic energy. In the case of an electromagnetic wave, these 2 degrees of freedom are derived from the electric and magnetic fields. Therefore, the average energy of each standing wave in the cavity is twice the average energy per degree of freedom. Next, Rayleigh multiplied the density of standing waves by the average energy to obtain the spectral energy density of the radiation in the cavity, which is precisely the Rayleigh-Jeans Law. Integrating this expression over all frequencies, Rayleigh finally obtained the total energy density of the radiation in the cavity as the following result. This result is known as the Ultraviolet Catastrophe, a term coined by Paul Ehrenfest in 1911. There is no limit to the number of times a standing wave can be subdivided into higher and higher frequencies, and assuming that each of the infinitely many possible higher harmonics had the same energy, led to the divergence of the total energy of the blackbody radiation to infinity, a result which is clearly unphysical.